Welcome to this lesson on AP Precalculus, Topic 1.9. In this video, we'll dive into the world of rational functions and a key feature of their graphs, vertical asymptotes. Our main goals are to learn how to find vertical asymptotes and understand the behavior of a rational function around them. First, what exactly is a rational function? It's a function that can be written as a fraction, where both the numerator and the denominator are polynomials. We write it in the form r of x equals p of x over q of x, where p and q are polynomials. Think of it like a fraction you're used to, but instead of just numbers, we have polynomial expressions. So, how do we find these vertical asymptotes? Let's break it down. The first rule is, if a number a makes the denominator 0 but does not make the numerator 0, then the vertical line x equals a is a vertical asymptote. This means you have a 0 in the denominator and a non-zero number in the numerator. Division by 0 is undefined, and graphically, this results in a vertical asymptote. Now let's consider the more complex case. What if a is a 0 for both the numerator and the denominator? In this situation, we must compare the multiplicities of that 0 in the numerator and the denominator. Multiplicity just means how many times a particular factor appears. A vertical asymptote occurs at x equals a if its multiplicity in the denominator is greater than its multiplicity in the numerator. If the multiplicities are equal, it's a hole in the graph, not an asymptote. So, to recap, you're looking for real numbers that make the denominator 0. If that number does not make the numerator 0, it's an asymptote. If it makes both 0, it's an asymptote only if it has a higher multiplicity in the denominator. Let's see what this looks like on a graph. What is the behavior of the function near a vertical asymptote? Near a vertical asymptote at x equals a, the denominator gets very, very close to 0. When you divide any non-zero number by a number that's almost 0, the result becomes a very large positive or a very large negative number. This means the function value r of x shoots up to positive infinity or down to negative infinity. Mathematically, we write this using limits. As x approaches a from the right, or the positive side, which we write as x arrow a plus, r of x approaches positive or negative infinity. The function gets arbitrarily large, either positively or negatively. Similarly, as x approaches a from the left side, or the negative side, which we write as x arrow a minus, r of x also approaches positive or negative infinity. So, on a graph, the function will get closer and closer to the vertical line x equals a, but it will never touch or cross it, because its value is skyrocketing. Let's put this into practice. We'll use a step-by-step process to find vertical asymptotes. Our first example is r of x equals the quantity x plus 1 divided by the quantity x minus 3. The first step is to factor the numerator and denominator completely. In this case, both are already simple linear factors, so there's nothing more to do here. Next, we identify the zeros of the denominator. We set x minus 3 equal to 0, and we find that x equals 3. This is our potential asymptote. Step 3 is to check for common factors. Are there any factors that are in both the numerator and the denominator? No, there aren't. So there are no holes in this graph. Finally, we determine the multiplicities. The factor x equals 3 only appears once in the denominator, so its multiplicity is 1. We also check the numerator and find that x equals 3 is not a 0 of the numerator. Based on our first rule, this confirms that x equals 3 is a vertical asymptote. Graphically, this means we have a vertical line at x equals 3, and the function's branches will approach this line without touching. Let's look at a second example that includes our second rule. Consider the function f of x equals the quantity x plus 4 times x minus 2 divided by x minus 2 times x minus 5. This one is already factored for us, so step 1 is complete. Let's move to step 2. The zeros of the denominator are found by setting each factor to 0. So x minus 2 equals 0 gives x equals 2, and x minus 5 equals 0 gives x equals 5. These are our potential asymptotes and holes. Now for step 3. Do we have any common factors? Yes, we have x minus 2 in both the numerator and the denominator. Because this is a common factor, there is a hole in the graph at x equals 2. For the remaining factor x minus 5, let's go to step 4. The factor x minus 5 appears once in the denominator. Does it appear in the numerator? No. So, according to our first rule, x equals 5 is a vertical asymptote. To quickly recap, the 0x equals 2 became a whole because it was a common factor in both the numerator and denominator. The 0x equals 5 became a vertical asymptote because it was a 0 of the denominator only. Let's explore an example where we need to compare multiplicities, which occurs when a 0 of the denominator is also a 0 of the numerator, and they are not common factors of the same multiplicity. Our function is g of x equals x minus 1 divided by the quantity x minus 1 squared. This is already factored, so step 1 is done. For step 2, the 0 of the denominator is clearly x equals 1. For step 3, we look for common factors. We have one factor of x minus 1 in the numerator and two factors in the denominator. Since we have at least one factor in common, we have a whole. In fact, if we simplify, g of x equals 1 over x minus 1. This means there's a whole at x equals 1. Now let's use the multiplicity rule to confirm what happens at x equals 1. In step 4, for the 0x equals 1, the multiplicity in the numerator is 1, and the multiplicity in the denominator is 2. Since the multiplicity in the denominator is greater than the multiplicity in the numerator, x equals 1 is a vertical asymptote. This example is interesting because it shows you can have a 0 that creates both a whole and a vertical asymptote. It's an asymptote in the simplified function after canceling the whole. Let's summarize everything we've learned with a concise table. This table will help you quickly determine what's happening at any real 0 of the denominator. First, if a number makes the denominator 0 but not the numerator, you have a vertical asymptote. Second, if it makes both the numerator and denominator 0, and they share a common factor with equal multiplicity, you have a whole in the graph. Third, if it makes both 0, but its multiplicity in the denominator is greater than its multiplicity in the numerator, you have a vertical asymptote. And finally, near any vertical asymptote, the function's value approaches either positive or negative infinity. By following these steps, factoring, finding denominator zeros, checking for wholes, and comparing multiplicities, you can confidently find all the vertical asymptotes for any rational function. Let's do one final comprehensive example to bring everything together. We want to find the vertical asymptotes and wholes for the function f of x equals x squared plus 5x plus 6, divided by x squared plus x minus 2. Step 1. Factor the numerator and the denominator. The numerator factors to x plus 2 times x plus 3. The denominator factors to x plus 2 times x minus 1. So our factored function is f of x equals the quantity x plus 2 times x plus 3, divided by the quantity x plus 2 times x minus 1. Step 2. Find the zeros of the denominator. From the factors, we see the zeros are x equals negative 2 and x equals 1. Step 3. Check for wholes. We see a common factor of x plus 2. Its multiplicity is 1 in both the numerator and the denominator. Since they cancel out completely, we have a whole in the graph at x equals negative 2. Now for step 4, we analyze the remaining 0 x equals 1. For x equals 1, its multiplicity in the denominator is 1. Is it a factor of the numerator? No, it isn't. Therefore, by our first rule, x equals 1 is a vertical asymptote. So we found that this function has one whole at x equals negative 2 and one vertical asymptote at x equals 1. This concludes our lesson on rational functions and vertical asymptotes. Let's quickly review the key takeaways. Today, we've learned the process for finding vertical asymptotes of rational functions. We covered how to find vertical asymptotes by factoring and how to differentiate between a vertical asymptote and a whole in the graph. We established that a vertical asymptote exists at x equals ae if x minus a is a factor of the denominator, but not of the numerator, or if its multiplicity in the denominator is greater than in the numerator. If multiplicities are equal, it's a whole. And finally, we saw that near an asymptote, the function's value will shoot up or down toward infinity. Practicing these steps will make you very comfortable with finding asymptotes and understanding the behavior of rational functions. Great work today.